Hello again. Again, we will focus on application of the micromotors. Application of the micro actuators. In that, we now study on the micromotors. In micromotors, there are two types of micromotors that what we discuss. We will discuss on the linear motors as well as rotatory motors. In linear motors, we will also use the electrostatic force, and in rotatory motors, also we will use the electrostatic force. The figure that what you are seeing will be focusing on the linear motors, and we also focus on this. This is all the explanation about the linear micromotors, and we also have explanation on the rotatory micromotors. So this explanation we will see in detail in the micromotors. So we are continuing with microactuation, and another example of microactuation that we want to take is micromotors. Well, what is there in the micromotors? Why do we need micromotors? Imagine that you want small micromotors or micro vehicles that you cannot see, but it has to move in a particular place, take some images and come back, a spying operation, or go in a place where human being cannot go and see, the small thin pipes, and investigate what is happening. Okay, or even you talk in medical terms, pass through the veins, pass through the nerves, go into the brain and look what is there in particular position. So there are plenty of such applications where it required motors, and motors are connected, let us say, to a robotic wheel, and a robot can go anywhere you want, but it requires the wheel which is connected to a tire like things, and you want the rotatory motions. So there are plenty of applications where you require a micromotor. Now if that is the case, how do I produce the rotating motion? So here we have an idea that what we have discussed just earlier, that I can make the movement of a a plane or a plate in one point to another point, that is a distance d, I can move by applying a electrostatic force on a parallel plate capacitors. Then if I can make continuously to move, then I may get some micromotor. So you have an idea on this. To begin with this, again you have to remember what is the fundamental equation that I am going to use will be this. Okay, again we are going to use this capacitance for two parallel plates, and we are going to focus on the force in the L direction. Look at the force in the L direction. So I am going to produce a force in the L direction, and in the L direction we are talking about width of the plate. Okay, now the width of the plate, that what we are talking is width of the plate that is required. You can see here width of the plate. Okay, from here to here. So this is the equation that fundamentally I will be using in order to produce a force in this direction L. So this is the fundamental understanding of this. So we will go back and see the arrangement that is required. You look at the arrangement here. So this arrangement you have to understand for producing the actuation force, primarily used for micromotors using an electrostatic force. So here we are going to produce the sliding force. Okay, the sliding force is on the force that is produced on the direction of the L due to the width of the electrodes, and it is in the direction normal to, inline to the plane, that is 180 degree along with the plane. Therefore, for doing such thing, you have to arrange the electrodes as you can see in the figure. So that if you arrange this in the figure, you see there are two sets of parallel base plates. You can see this is the fixed set of electrodes which is on the darker one, and you have a moving set of the electrodes on top of this is here. This is the gap that exists between the two electrodes. So each of these two sets of these base plates having a number of electrodes which are all conducting plates. You can see there is a number of electrodes on this direction L. So the A1, A2, A3, or A, B, C, D, sorry, A dash, B dash, C dash, D dash, and A, B, C, D. These are all the number of electrodes. And these electrodes, of course, is having the length, and this length, we use the word not L here, W, because we are talking of producing the force which is in line with the plane, that is in line with the plane, and it is the equation that what we are going to use is FL, or on the length of this one. So FL is having the equation which uses the width of the electrode. So for that reason, the length of this electrode is now given as a width W, because W is used in the equation. For that reason, FL equation, W is used. So we are calling this electrode is having the length W. Now look at the bottom base plate is also having the width of the pitches of W. So this is also, look at the bottom. This is all W, and you see this is W, 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 all these are W. Okay, so you have this W thing here, and these okay, let me stop here for a while. So again, these electrodes are having, of course, the length W. So you are talking length as a W. The bottom base plate has an electrode of pitch W. This is also a pitch W, that is for A. This is for A dash. So the top base plate has slightly different pitch. You can see the distance between these two. Okay? This is the electrode distance, and what it is maintained is here is W plus W3 in the case of A dash and B dash, but you look at this in case of A and B, it is not W plus W3, it is W. So you see this arrangement, you have to do it. Here it is W, here it is W, and here the distance between these two is W plus W3. Why? Because you see the position that you have started here. In the position that you have started here will be a gap or a distance, moving set of distance. This is a moving electrode, will be W by 3. So the starting is W by 3. Okay, so if you look, and starting is W by 3, at the same time the distance between A dash and B dash is not W, it is W by 3, but the distance between A and AB is W. This you have to understand in arrangement of this linear motion electrodes. So you have two sets of these base plates which are misaligned. Okay, so this we call it as a misaligned electrodes, and misalignment value here is W by 3. That is 1/3 of the width of this, the length of this plate, that what you are electrode plate that you are taking. You make it relative, and you make this W by 3. And you may set this bottom plate as a stationary. So this is the fixed plate or a fixed set of electrodes. So that top plates is the sliding plate, or the plate that is going to move in the direction of the horizontal plane. Now once you energize this pair of A and A dash, so you need to connect the potential for this and this through the voltage. So you energize this pair of A and A dash. This will cause the motion of the top plates moving from left until A to A dash. And how much it will move? It will move until A and A dash will be fully aligned. So you can see here, this will try to align this here, so that this is the difference what you are having. So A dash and A will get aligned here. So at that moment, now watch what happens to the B and B dash. Look at this B and B dash. If this moves by W by 3, still this is left with the W by 3 with respect to this B. So there exists again a gap of W by 3 once this moves by W by 3. So this is left with a gap of W by 3. So this position that was there, now it exists here as a new position for this. So again, these are all misplaced. then again by W by 3. So again you energize it, what happens? This plate will move, so that this will align here. B and B dash will align. Of course this will be in line with the plane. So this will get moved. The whole set will move. Now look at what happens at C and C dash. The distance is such that again if this gets aligned, B and B dash get aligned, you're going to end up with C and C dash misaligned with W by 3. And again you energize, and C and C dash will get aligned, but you see D and D dash will get the misalignment. In this way you can see the continuous misalignment exists, and energizing will make the motion, and it keep on continues to move until the pair D and D dash. So what we are going to do this is, we have to carefully arrange the electrode in the top and bottom plates, and the proper pitch need to be needed, and you have to apply the amount of the voltage, that is the electrostatic force that is required to provide a relative motion to the two set of these plates. So you can see this misalignment will give you a smooth movement of the motion, and of course if you rotate this circularly, this is a set of plates, and if you rotate this circularly, in a round circularly, then what you get is a stepper motor or a rotation motor type of one, which works with the same principles. So if you keep this in a rotational force direction, what you understood this, but if you turn this and bend this into this one, then you can get the continuous movement in the rotational direction. So this is what the rotating or rotatory step motion motors, which involves two sets of electrodes, which you can see here, this part. Okay, one set is called as a rotor, other set is called as a one set is called as a rotor, rotating one, and another one is the stator. Now look at the gaps that is arranged. Suppose, let us say, this is the initial misaligned, and look at the gaps that is existing here, existing here, 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 and here. So this is the careful arrangement that design engineers can do this, and if you can design the positioning of this, okay, one is the rotating electrode on this side, which is a rotor, and non-rotating, which is a stator, and if you properly maintain this alignment with proper degrees, you can beautifully have a stepper motor effect. And this rotatory motor is driven by the electrostatic force, and electrodes are installed in the outer surface of the rotor poles, and the inner surface we call it as a stator poles. And in this case you will have pitches which is maintained in the rotor poles and stator poles are misaligned, okay, the way in which you have generated in the case of electrodes, that what we discussed earlier. Then you also have to notice some things like the number of these poles. Okay, 1, 2, 3, 4. You measure 1, 2, 3, 4. What you have to do is you have to maintain the ratio of the poles in the stator to those in the rotor. That will be 3:2. Similarly, you have to maintain an air gap. You can look at this air gap. You have to maintain an air gap between the rotor and stator poles, normally about 2 micrometers. Then the outer diameter of this one is also calculated. This, if you see the outer diameter from this one, from the center, okay, to the radius, 2 times of the radius, you will get the outer diameter. Normally it can be an example for 100 micrometers, and the length of the rotor poles is about 20 to 20. So you can also calculate the length of the poles, around 20 to 25 micrometers. Now when you design such type of rotatory thing, this is the rotor, okay, this is the rotor, and this is the what comes out in my direction is the shaft. That is where you can connect your tire, you can connect something that is going to take the load of the object. So if you look at practically, it looks like this. This is work done by some companies, where you can see here with all the dimension on the bottom. You can see here, this is the stator and this is the rotor, and you can also directly connect this from here vertically up, and that can be rotatory movement. But if you connect that, what is the speed that what you get is the slow speed due to the rotor movement. But let us say you want to have a higher speed, then you can have a gear, and this gear is a transmitting gear, and you can see if this is rotates, this will rotate at higher speed, this will be rotated at the lower speed. This is just like a vehicle moving in the first gear, lower speed, but takes more load, and a higher gear takes the lower load but higher speed. So for such applications you can have this, but one problem that exists is this bearing. This is all connected, physically it is connected, and there will be a bearings wear and tear, and lubrication need to be made. Lubrication is, if you probably if you are driving a two-wheeler, if your bearing is gone, you will get your two-wheeler handle will start rotating, which is called a wobbling. Or if your vehicle is moving, if it is a misalignment wheels, then the vehicle itself will go on left side and right side when you are moving forward, and this is undesirable effect, which you call it as a wobbling. Such rotational speed wear off and will be there. Probably you have to design this for around 10,000 revolution and scrap, sent to the scrap. So you have all this problem in the case of a micromotor. It's an area of research. One can work on how to reduce the friction, wearing, lubrication, and these are all the critical area of research that one can study. And a lot of publications are available for one who can show an interest in this micro tribology. Tribology is the area of smoothing, making this, so itself is an area. So next what we see is we discuss about the micro valves.